Jim warned you there probably wouldn't be time for questions, but I do really appreciate the quality of the information you folks just put out. The title of this workshop was Research and Monitoring. There's a tremendous amount of really important monitoring going on out there, particularly in the human environment, that we all need to be aware of and think about how it interacts with the biological, you know, the dirt, the bugs, the trees, the water, other stuff that people are studying so intensely and reporting on here. So thank you guys very much. Moving on then to the next talk will be Michele, I'm not going to say your name right. Buonanduci. She's going to be talking about examining wildfires from other regions and fire regimes yields insights into future patterns of burn severity in Western Cascadia. So help me welcome Michele to the stage.
Awesome. Hi, everyone. My name is Michele. I'm a graduate student at the University of Washington. And today I'm going to be talking about examining wildfires from other regions and fire regimes in order to gain some insights into future patterns of burn severity in Western Cascadia. So to start, I'd like to acknowledge my co-authors on this work. Dan Donato and Josh Holofsky are with the Washington DNR. Maureen Kennedy is with the University of Washington Tacoma, and Brian Harvey is with the University of Washington. I'd also like to acknowledge the funding sources for this work and the support provided by lots of different people. So the focus of this research project is the infrequent high-severity fire regimes west of the Cascade Crest in western Washington and northwestern Oregon. So this study region is highlighted here. We're calling it Western Cascadia, and it's a focus of a number of ongoing research projects that my co-authors and I, along with a number of collaborators and partners, are working on. So as the potential for fire increases in Western Cascadia, the goal of these projects is to gain a better understanding of the characteristics of wildfire in this region. So as you all know, due to the infrequent nature of fire in this region, fire has been characteristically rare in recent decades in Western Cascadia. However, the 2020 fires really highlight the role that fire has historically played in these landscapes and the role it will continue to play in the future. So as climate continues to warm and area burned in Western Cascadia potentially increases, there's a lot of ongoing research parsing out the climate drivers of fire size in this region. So it's generally understood that small to medium-sized fires may be driven by increasing drought conditions, whereas the largest fires we see are generally driven by strong, dry east wind events coinciding with those drought conditions. So some of our collaborators are currently working on evaluating these drivers and determining the relative likelihood of small versus large fire events moving forward in Western Cascadia. And it's really important to consider the size of future fires, but it's equally as important to consider the spatial patterns of those fires and what they might look like. So the size and also the shape of high severity burn patches really sets the template for post-fire forest recovery. That's primarily because the interior portions of those large high severity patches can potentially be really far from unburned live trees following fire, and therefore really far from seed sources. Because of this, these high severity patches are often where management intervention is most needed. So things like replanting with tree seedlings, also landslide hazard assessments because these areas are really prone to erosion and debris flows. And while these patches are a real concern for managers working to protect forest health, it's also worth noting that these areas are where complex early seral pre-forest habitat forms, and that habitat is critical for a wide range of wildlife species. Indigenous communities in Western Cascadia historically used fire to manage these landscapes and promote that pre-forest habitat because it supports a number of culturally important plant species, including huckleberry, which is shown here. So all of this is to say that anticipating the spatial patterns of burn severity in this region, and in particular those high severity patches where most trees are killed, is really important, not only because it impacts forest health, but also because it impacts a wide range of ecosystem services. When it comes to anticipating these patterns, however, the challenge is that predicting spatial patterns of burn severity for a given landscape is really difficult. This is because spatial patterns of burn severity are driven by a complex mixture of drivers, so things like vegetation and fuels, topography, and fire weather, which can be highly variable. More generally, however, thinking about the spatial structure of fires, you can imagine that as fires increase in size, the potential for large high-severity patches also naturally increases or scales upward. So we refer to this as a scaling relationship, and when paired with projections for overall area burned and fire size distributions, these scaling relationships can be used to infer potential future fire impacts. So understanding the range of patch structure that might be expected across a range of fire sizes in Western Cascadia is going to be really useful for anticipating and planning for those impacts. Going back to this figure, however, the challenge is that we have really limited data for the spatial structure of burn severity in Western Cascadia. So using the satellite fire record, we have only 31 Western Cascadia wildfires for which we're able to characterize those spatial patterns of burn severity. This really limits the statistical power that we have to describe these spatial patterns and how they might vary with increasing fire size. So fortunately, we can look to a broader geographic region. So here we have the forested ecoregions of the broader Northwest US, where fire activity has been much more frequent within the satellite record. So by comparing the limited data that we have for Western Cascadia to these other forested regions, we can evaluate whether the spatial patterns of wildfires in Western Cascadia fall within the range of patterns we're seeing in these other regions, as well as other fire regimes. So as many of you know, fire regimes vary widely across the Northwest, with those infrequent high-severity regimes being fairly prevalent both in Western Cascadia as well as in subalpine forests of the Northern Rockies, for example. So if burn severity scaling relationships in Western Cascadia appear comparable to these other fire regimes in the Northwest, then data from those comparable regimes can be harnessed to supplement the really sparse empirical record that we have for Western Cascadia. So that brings me to the questions we're working to address, which are first, how do burn severity scaling relationships in Western Cascadia compare to other fire regimes across the Northwest? And then building on that, how might the range of burn severity patch structure in Western Cascadia vary depending on the size of future fire events? And I'd really like to emphasize here that the goal of this research is not to be able to predict specific spatial patterns that we might expect in specific landscapes, but rather at a broad regional scale to put quantitative bounds on the type of wildfire patterns we might expect to see in this region. So getting into some of the data processing for this work, our broader study region, as I said, is the Northwest US. And we have assigned each fire event within that region the primary fire regime as mapped by land fire within that fire's perimeter. And then here are Western Cascadia fires for comparison. So for each fire, we're using Landsat satellite imagery to generate maps of RDMBR, which is a satellite index of burn severity. We're then using statistical models to classify that burn severity index into two burn severity classes based on the proportion of trees likely to have been killed. So we have our high severity class where most trees are killed, and then our low to moderate burn severity class. Combining each classified burn severity map with available land cover data, we are then generating maps of distance to potential seed source within the interior portions of those high severity burn patches. Finally, we're using our classified burn severity maps to calculate high severity patch size metrics for each fire, and we're using our distance to seed source maps to calculate high severity patch structure metrics. So what do I mean by that? First, thinking about high severity patch size, you can imagine that for each fire event, we have a distribution of patch sizes. So in this figure here, we have patch size along the x-axis, and then the inverse cumulative probability or proportion of patches along the y-axis. As an aggregate metric, we're using an area-weighted mean of all of those patch sizes, which is going to fall towards the upper end of that distribution. And then in addition to that aggregate metric, we are fitting patch size distribution shape parameters, describing the overall shape of the distribution, and in particular, the relative prevalence of small versus large patch sizes. Next, thinking about the structure of high-severity patches, for each fire, we have a distribution of distance to potential seed. So here in this figure, we have distance to seed along the x-axis, and then inverse cumulative area on the y, both in terms of hectares, as well as a proportion of the total high-severity burned area. As an aggregate metric, we're using the total area exceeding a distance threshold of 150 meters to define core area. That's because 150 meters is the probable seed dispersal distance for a lot of conifer tree species. Then in addition to that aggregate metric, we're also fitting a distribution shape parameter here again, describing the shape of this distribution, in particular how quickly it drops down to 0 with increasing distance. So getting into some of the analysis and results. First, to get you oriented to these spatial scaling relationships, here we have area-weighted mean patch size plotted against fire size, and I'll note these are both log transformed axes here. And then we have our 3 fire regime groups within the Northwest. So that frequent low-severity regime on the left, our mixed-severity regime in the middle, and then our infrequent high-severity regime on the right. For brevity, in the next couple slides, I'm just going to be showing the aggregate spatial metrics and not those distribution shape parameters, but we did also evaluate those. So for each fire regime, we're fitting smooth curves to the relationship between fire size and each spatial metric, and we're using non-parametric quantile regression to do that. So the bold line that you see here in these figures represents the 50th percentile of the response. The inner shaded band represents the middle 50% of the response, and then the outer shaded band represents the middle 95% of the response. So this allows us to characterize the full range of variation in patch metrics across that range of fire sizes. So a couple of takeaways here before I show you how Western Cascadia stack up. First, as you can see, fire regimes across the Northwest demonstrate really clear and consistent scaling behavior. So as fire size increases, patch size also consistently increases. And then within these fire regimes, we found that these scaling relationships did not differ substantially across space or time. So either by geographic region within the Northwest or by year or time period within the satellite record. And while it's possible that these scaling relationships might change in the future, the consistency that we're seeing within the contemporary record suggests that they can be used to infer near future patterns of burn severity we might expect within these fire regimes. So how do our Western Cascadia data compare? Here we have the Western Cascadia fires overlaid over the broader Northwest fire regimes. And we can see that visually the Western Cascadia data appear really consistent with that high severity regime group. And we can confirm quantitatively that that high severity regime from the broader Northwest offers the best fit for our Western Cascadia fires, which is absolutely what we expected to find here. Then looking at core area, our core area metric, we have a similar story here as well, both in terms of the consistency of those scaling relationships. And then once we overlay our Western Cascadia data, again, we see that the high severity regime from the broader Northwest offers a really good fit, which we can confirm again quantitatively. Okay, so bringing it back to our first research question, what we have found so far is that the Western Cascadia data appear consistent with other high-severity fire regimes in the Northwest. So this suggests that we can take data from those other high-severity regimes to supplement the really sparse empirical record that we have for Western Cascadia. And what's great about that is that it enables us to do a simulation study exploring potential future fire impacts. So here we have the combined data set now for Western Cascadia and the Northwest high-severity regime fires for our core area metric. So at any given fire size now, we can simulate potential outcomes by drawing from that range of variation that we've quantified in this scaling relationship. So we can simulate potential core areas for very large fires, say 100,000 hectares in size, or moderately large fires, say 10,000 hectares, or smaller fires, say 1,000 hectares, or really any fire size in between. And we can do that, again, by simulating from this scaling relationship for the combined high-severity data set. So building on this, we set up a simple simulation study to help illustrate how the range of potential future fire impacts in Western Cascadia might vary depending on the size of future fire events. So we can ask, assuming 1 million hypothetical hectares were to burn in Western Cascadia, either in a really extreme fire year or a series of fire years, what are the potential impacts if this area were to burn as 10 very large fire events, each 100,000 hectares in size, or 100 moderately large fires, each 10,000 hectares, or 1,000 smaller fire events, each 1,000 hectares in size? Because remember, an area of active research is parsing out the climate drivers of fire size in this region and determining the relative likelihood of small versus large fire events moving forward. And this research is meant to be really complementary to that effort. So getting into some of the results from this simulation study. So here we have our fire size distribution scenarios along the x-axis. And then we have the total core area aggregated across those fire events along the y-axis. So looking at some of these results, here we can see that if those 1 million hypothetical hectares are burned in large fire events, either 100 moderately large or 10 very large fires, we're looking at a doubling or more in total core area as compared to that smaller fire size scenario. Remember here, our core area metric is that total area exceeding a distance of 150 meters or more to the nearest seed source. So in addition to that aggregate metric, we can also simulate the full distance to seed distributions using that distribution shape parameter that I mentioned earlier. So here we have distance to seed along the x-axis. And then inverse cumulative area, so the total high severity burned area exceeding each distance threshold along the y. So looking at these results, we can see that as fire size distributions increase, the tails of these aggregate distance to seed distributions become heavier. So looking at a distance threshold of 750 meters to seed, for example, we actually have a 10-fold increase in area exceeding this threshold, moving from the smallest fire scenario to the largest. Finally, we can also simulate patch size distributions, again using the distribution shape parameters that I mentioned earlier. And we can look at this a couple of different ways. So here we have high severity patch size along the x-axis, and then an inverse cumulative proportion or frequency of patches along the y-axis. So looking at these results, not surprisingly, we see the occurrence of increasingly large high-severity patches with increasing fire size distributions. However, it's interesting to point out that actually most patches by frequency or number are relatively small. So 90% of patches actually fall above this dashed line here, and the median patch size across all scenarios was close to 3 hectares. Another way that we can look at this, though, is that instead of considering the proportion of patches, we can consider the proportion of the total high-severity area contributed by those patches. So now we have, again, patch size on the x-axis, but this time we have inverse cumulative proportion of total high-severity burned area on the y. So looking at these results, we can see that in the moderately large and very large fire scenarios, the contribution of those large patches to the total high-severity burned area is substantial. So on average, individual patches of high-severity burned area exceeding 1,000 hectares in size made up around 50% of the total high-severity burned area in that moderately large fire scenario, and around 70% or more in the largest fire scenario. So in these larger fire scenarios, the impact of these very large patches on the landscape is substantial. Okay, so wrapping things up with some key takeaway points, we found that burn severity patterns in Western Cascadia are comparable to other high-severity fire regimes across the Northwest U.S. We demonstrated with a really simple case study scenario that scaling relationships can be used to simulate potential future burn severity patterns given projections in total area burned and fire size distributions. And then finally, we found that even if total area burned were to stay the same, shifts in fire size distributions towards larger fires will lead to increasingly large high-severity patches with interior areas that are increasingly far from unburned seed sources. And that, of course, has really important implications for how we manage forests in Western Cascadia, both in terms of tree regeneration as well as early seral habitat in an era of increasing fire activity. So with that, I'm happy to take questions. If I have no time, okay, no worries. Thanks, everyone. Come find me later if you want to chat.